Alright, this recording is for Project Help for Unit 2, Lesson 8. Lesson 8 deals with what I call the case of the stolen monkey. So it's about a monkey named Mac that's stolen from the zoo. I kind of thought this was a silly crime until I did some research. And apparently some people actually steal monkeys, as shown on the picture on the left. Alright, so question 1. The thieves were 5 miles away from the scene of the crime after 12 minutes, which is a fifth of an hour. After 30 minutes, or a half an hour, the thieves were 15 miles away. Write two equations in point-slope form that describe the distance the thieves are away from the crime scene based on the time that passed. Alright, so what is slope-intercept form, or point-slope form, excuse me. So here's point-slope form, y minus y1 equals the slope times x minus x1. The y1 and the x1 are some point on the graph, and the m is the slope. Remember, the y and the x are always part of the equation. Alright, so we need 2 points in order to find the slope of a line. And in this case, our points are going to be written first with the time as the x variable and distance as the y variable, as shown here. So one of our points is right here, 1/5 of an hour. The thieves are 5 miles away. So we have the coordinate 1/5 and 5. The next point that we're given is that after a half a mile, the thieves are 15 miles away. So that's 1/2, 15 as an ordered pair. The reason why we needed to list out those ordered pairs is so that we can use the slope formula to find the slope of this line. Alright, so in this case I'm going to take the 15 minus 5. That's our y2 and y1. This just means the y-coordinate of point 2 minus the y-coordinate of point 1. And then we're going to subtract that from the x-coordinate of point 2 minus the x-coordinate of point 1. So then we go ahead and we simplify some fractions. So we get that 10. We have to get equivalent fractions on the bottom, so we have the same denominator, so we can subtract the fractions. We have 10 divided by 3/10. In order to calculate that, remember, we multiply by the reciprocal. So I take this 3/10 and I flip it, we get its reciprocal, and then I'd have 10 times 10, which is 100, over 3 on the bottom. And then finally 100 divided by 3 is 33.3. Right, so then it wants us to write two equations. Well, we can write really an infinite number of equations giving an equation in point-slope form, because we can put any point in we want for x1 and x2, and y1 and y2. In this case we have 2 points. So I can write two equations. They both have the slope of 33.3. And then we can write with the first point, y minus 5, the y-coordinate, equals 33.3 times x minus the x-coordinate, which is 1/5. And then we can use the other point to write the other equation. So we just plug in its coordinates for the y1 and the x1. So there's two possible equations you can write using the information they gave us. Okay, so question 2 asks, what's the slope of the line represented by this equation as you selected? Well, when we found out the slope, right, that represents the speed of the vehicle, or how fast the monkey is moving away from the crime scene. And that's this m, that's in front of both of these equations. So that's just right there already telling us 33.3, which we just figured out. And then what does it represent? Well, it represents the speed of the vehicle that the monkey's in, or how fast they're traveling away from the zoo or the crime scene in this case. And it's in miles per hour. So you might be wondering why they had to go ahead and convert. Remember, from this problem, they had to tell you 12 minutes was a fifth of an hour, and 30 minutes was a half of an hour. That's because when we calculate the slope, we want that number to be in miles per hour, so we need some consistent units. If we went ahead and used the minutes, right, instead of the hours, then we would have a different slope here, and it would represent not miles per hour, but it would represent miles per minute. And we usually don't talk about speed in miles per minute, so that's why they go ahead and give you the fraction of an hour that the minutes represent. Alright, so in this case that 33 does represent 33 miles per hour. So question 3 says, the police are tracking the thieves for a while, and after 1 hour the location is 35 miles away, and after 75 minutes or 5/4 of an hour, the location is still 35 miles away. Then we want to write an equation in point-slope form that represents the distance the thieves are, assuming they are traveling in a linear pattern. All right, write the equation in point-slope form. All right, so since they are, in this case, after 1 hour, at still 35 miles away, and after 75 minutes, or 5/4 of an hour, still 35 minutes away, we know they're not moving. Right? They must be staying still. That means the slope in this point-slope equation is going to be 0. But just to show you that, let's go ahead and do what we did with the last problem. Let's go ahead and write out the points. Remember, the points are always time as the x variable, then distance, right, as the dependent variable. So 1:35, that's after 1 hour, they're 35 miles away. After 5/4 of an hour, they're still 35 miles away. And if I use the slope formula to calculate the slope, notice that in the numerator, we're going to get 35 minus 35, which is 0. And then it doesn't really matter what we get on the bottom when we subtract the x coordinates, right? Because 0 divided by anything is still going to give us 0. All right, so there's two possible answers that you can type in for this question. One of them is here. So I'm going to pick the first point. I'm going to go ahead and plug in the y for the y1 and the x for the x1. And we know that the m, the slope, is 0. So without simplifying it, that's what they want you to type in, right? Just that equation there. There's another possible equation you could write in point-slope form, and that's with using the other point they gave us. So we're still going to have after 35, they're 35 miles away for the y, but then the hours here are going to be 5/4 of an hour. Notice that if we simplified both of these equations, that means go ahead and distribute that 0 or multiply by 0 gives us 0. We would still end up with the equation y equals 35 in slope-intercept form. And that makes sense, right? Because it's a horizontal line since the thieves are not moving. So lesson 8, question 4 asks, after a little while, the thieves start changing position again. Okay, so now after their little break where they stopped moving, now they're going to move again. And so they were still at the 35-mile mark after 90 minutes, or 3/2 of an hour, but then they started to travel at 60 miles per hour. So now they want us to write an equation in point-slope form of a line that represents that situation. So remember, here's the equation. I always like to start with the equation itself. And here's the equation for point-slope form. We need to know the slope, and we need a point on the line. All right, well, they tell us the slope. We know the slope because the slope, when we're talking about in a context of distance and time, the slope is the speed or the rate or the miles per hour. All right, that's how we just did it in question 2 as well, right? When we calculated that 33.3, we were finding the miles per hour that the thieves are moving. Here they tell us that. It's already 60, so we already know that the slope is 60. Good, now we just need a point. We just need any point on that graph to plug in for our x1 and y1 into the equation. All right, well, we have one. They tell us that after 3/2 of an hour, all right, or 90 minutes, that the vehicle is at the 35-mile mark, or 35 miles away from the scene. All right, since we want to have our slope in miles per hour, we're going to use the hours, the 3/2 of an hour, not the 90 minutes there. All right, so now we have our point, we have our slope, we can plug those values into the equation. We get that y minus 35 equals 60 times the quantity x minus 3/2. And finally, question 5 asks you to write how you know that the two equations in point-slope form are the same, or how would you know that? In general, it wants you to write a little discussion about it. Well, just to illustrate how I would do it, I'm going to write two different point-slope equations here, and I'm going to go ahead and prove to you that they are the same line. All right, so there's a couple of ways we could do it. One way, right, is to go ahead and rewrite each of the equations into slope-intercept form and then show that they are the same. Another way to do it would be to take turns plugging in the points that they each have in their equation into the other equation and see if you get a true statement. So there's two ways. Let's do method one. So this is what you could talk about in this problem. Method one would be to change them into slope-intercept form. So let's change them or convert them into slope-intercept form. That'd be one way to do it. So for example, in this top equation that's in point slope form right now, I can go ahead and simplify it and get the y by itself. That's what we mean by getting it in slope-intercept form. So go ahead and I'm going to distribute that -2, and then I would have that y minus 3 is equal to -2x plus 4. Then finally we want to get y by itself, so then I would just add this 3 to both sides. So then I'd have that y is equal to -2x, and I can add numbers to numbers, so 4 plus 3 would be 7. Okay, so now I would know that this equation down here is the same line. If when I change it into slope-intercept form, we get the exact same equation. Alright, so then in this case, I'm going to go ahead and distribute that -2. Oh, and by the way, there's a little shortcut I can look at. They have to have the same slope, right, to be the same line. So the very first thing I would verify is that they both had the same slope, which is this number in front of the x-coordinates here, right? In this case, this coefficient. And they are the same in this case. But that's not enough to prove that they're the same line. That just proves that they're parallel. So that's why I'm going through this process here of changing them into slope-intercept form. Alright, so once I distribute the -2 on the right-hand side of the equation, we get y is equal to -2x plus 2. And then now notice that my next step to get y by itself would be to add 5 to both sides of the equation. So then I would get that y is equal to -2x plus 5 to that 2, so 2 plus 5 is 7. And then now look at the two equations here. They are identical. And that's how I know that these two represent the same line. Another way to do it would have been said to look at equation 1. You remember that what's with the x is the x-coordinate and what's with the y is the y-coordinate. So what this implies is that the point that they used to write this equation was the point 2, 3. Alright, so if I want to know that these two really represent the same line, first I'm going to verify they have the same slope. They do. Then I can take this point 2, 3, which is suggested by the top equation, and plug it into the x and the y in the bottom equation and see if we get a true statement. Alright, so from the top equation I get the point 2, 3 on that line. I'm going to plug it into the bottom equation for the y and the x and see if we get a true statement. So where this y is here, I'm going to write 3 instead. So is 3 minus 5 really equal to -2 times the x-coordinate, which is 2, minus 1. Alright, so on the left-hand side, this simplifies to 3 minus 5, or -2. On the right-hand side, we get -2 times 1, and -2 times 1 is -2, so -2 does in fact equal -2. Since we get a true statement, then I conclude that these two are in fact the same line. You could also vice versa, right? Take the point that is indicated on the second equation, which is the point 1, 5, and plug it into the top equation and verify that you get a true statement there as well.